Welcome back, buddy. This is episode number 5 of Attentions in Transformer series. In the last 4 episodes, we fully unpacked the QKV attention block. Since attention is the real core of the transformer, today's topics, multi-head attention and the feed-forward network, are lighter extensions built on top of that foundation. To ease into today's journey, let's smoothly transition from what we already know about attention to how these new components build on it. If you followed along in the last episodes, you may already feel this intuition. Attention works like an interview. Each token interacts with the others by asking questions, providing key information, and sharing answers. In an interview, the interviewer asks questions, and each interviewee responds based on their characteristics. In attention, the query plays the role of the question. The key explains what each token represents, and the value provides the actual information. Attention repeats these 3 steps: asking, ranking relevance, and combining answers. Thanks to matrix multiplication, every token is processed simultaneously, which is a major reason transformers are fast and efficient. As you know, the entire attention mechanism begins with 3 sets of vectors: queries, keys, and values. Each token creates its own Q, K, and V through linear projections. Each row in the query matrix represents what a specific token wants to know. Token 1 has its own question, token 2 has another, and so on. Questions need something to compare against. That's where keys come in. Each token has a key that indicates what kind of information it offers. The dot product between a query and a key gives the relevance score between 2 tokens. Values are the actual information the model will mix together. After determining relevance through query-key comparisons, attention uses these values to compute the final output. Let's put them all together. First, we compute QK transpose. Every query is compared with every key. Softmax turns those comparisons into scores. Then we multiply by V, combining values according to how relevant they are. The result is the updated representation for each token. This is practically the entire essence of how the QKV attention mechanism works. However, this attention mechanism relies on just one aspect or perspective of the input. Transformers don't rely on just a single viewpoint. They use multiple parallel attention mechanisms, each capturing different types of relationships. To understand what and why, we need to keep going. The important thing to note here is that the standard QKV attention formula gives each token its own single, unique question. Every token asks one specific question, and that question is different for each token. But relying on just a single question per token limits how deeply the model can understand the context. For richer insight, we need multiple questions per token. So now we step into a multidimensional interview. Instead of relying on one question, we ask several different kinds of questions. Each question highlights a different perspective of each token. So now we step into a multidimensional interview. Compared to the earlier interview, where each token could be asked only a single question, here we introduce several different kinds of questions. Each one highlights a different new perspective of the token. To support multiple questions, we naturally extend the single queue setup into multiple queue matrices. Each matrix forms its own set of queries, allowing each token to ask question 1, question 2, and so on. Questions alone aren't enough, are they? Each new question needs its own set of keys as well. Different keys reveal different aspects of what a token can offer. And of course, we need multiple sets of value matrices. Each value matrix carries a different type of information, so the model can blend insights from several perspectives. Each set of Qs, Ks, and Vs produces its own attention output in parallel, that is, at the same time. Every one of them captures a unique viewpoint. After computing them independently, we combine their results to build a deeper and more expressive representation. By merging all attentions focusing on different perspectives, we get a much richer final output than single-head attention. Don't forget, each attention mechanism runs independently, allowing the model to process multiple attention calculation at the same time. This multi-dimensional interviewing gives transformers the power to understand relationships from many angles simultaneously. Now that we've explored multiple perspectives through attention, it's time to introduce the next major part of the transformer block, the feed-forward network, or FFN. This component doesn't retrieve or compare information. Instead, it creates brand new features. Up to this point, we've only dealt with attention. But a transformer block actually applies two different transformations. First, with multi-head attention, and second, with the FFN. After the contextual mixing at attention stage, the FFN further transforms each token individually to generate even deeper representations. Why do we need this second type of transformation? If attention already mixes information, what's missing? Let's break down the limitations of attention. First, attention retrieves, compares, and mixes information, but it doesn't create anything completely new. As we've discussed in episode 3, it's like searching a database. You can retrieve, reorganize, and blend what are there, but you can't invent new features. Next, attention heavily focuses on relationships between tokens. It's great for understanding context, but not for reflecting deeper internal transformations within each token itself. Think of it as lacking introspection. Last but not least, attention relies on linear transformations. While powerful, linear methods alone can't express complex patterns. To give the model nonlinear expressive power, we need something more. The FFN solves these issues. It applies a linear transformation, followed by a nonlinear activation function. The weight matrix of FFN isn't there for measuring relevance like attention score. Instead, it generates brand new features of each token without retrieving or reorganizing any existing information. This gives the model a chance to expand and reshape information after the attention step. Moreover, unlike attention, the FFN processes each token independently. There is no cross-token communication here. Every token gets transformed on its own, which adds depth without mixing contexts again. Finally, the FFN uses activation functions to introduce non-linearity. This is what unlocks expressive power, letting the model detect and build complex patterns beyond what linear transformations can do alone. Let's recap. A single transformer block is made of two major components, the multi-head attention layer and the feed-forward network layer. Together, they form one complete cycle of understanding and transformation. Here you can see how everything fits inside one transformer block. Multiple attentions run in parallel. Their results are combined, and then the FFN further transforms the output token-wise. This block becomes the basic building unit of the entire transformer model. In the next episode, we'll complete the full stack by adding the remaining essential pieces like positional embeddings and normalization. See you there!